Okay, so I think we are good to go. Remember, everyone, this is being live streamed, recorded, and distributed. This lecture is about coupling cells and fields and chemotaxis, which is one of the ways cells can communicate at short and long distances using fields and promote movement or tissue rearrangement from fields. Okay. And again, my name is Pedro from Brazil. In this module, we're going to cover cell movement and gradients, chemotaxis specifically, issues when understanding chemotaxis, because the biology behind chemotaxis is very complicated. How to model simple chemotaxis in CompuCell3D, specifications in CC3D-ML, specifications in Python, adaptation of Lambda chemotaxis. So we will have a parameter for chemotaxis, and we will see how we can adapt this parameter for different types of fields, configurations. Also some exercises. Hopefully we will have time to show you the bacterium neutrophil simulation. And you can, if you already know how to implement chemotaxis, you can try building the bacterial neutrophil simulation yourself. So a quick summary of cell movement. We have different types of cell movement. For example, amoeboid for amoebas, which is filopodial. We also have for eukaryotic cell the lamellipodial movement in substrates. Okay, so this is promoted by actin polymerization and depolymerization. Okay. And ingredient cells can have their movement respond to external field gradients by chemotaxis, for example, which is very, very common. But you have many other types. For example, durotaxis, in which cells move according to how hard the tissue is. So, for example, moving to regions of higher rigidity or lower rigidity, for example, in metastasis. Also, substrate adhesion and molecules that are placed over the substrate. This is called apotaxis. Also, there is galvanotaxis or electrotaxis for electrical field, although it's not clear how the field itself interacts with the cell and how the field interacts with the ions that interacts with the cell. So electrotaxis is very complicated. There's also thermotaxis, which is studied, for example, it is important in long range communication, for example, in sperm guidance. Phototaxis, which is light intensity gradient, rheotaxis and negative rheotaxis if you have an external fluid flow, and chemotaxis, which is when you have a chemical solute in the medium, and then this becomes a signal for the cell. Okay, so not all, but many of those types of taxis can appear, for example, in metastasis, immune response, angiogenesis, wound healing, sperm guidance, etc. So specifically about solutes, chemical gradients, we refer to the bias in the motion of the cell as chemotaxis in this case. But there are two main ways that cells can respond to chemical fields. One is the chemotaxis, and other is the chemokinesis. So the difference between chemotaxis and chemokinesis is that chemotaxis is when the cell senses the gradient inside along the cell, and then already know where to move. While in the chemokinesis case, the cell doesn't have enough size to feel the gradient, to measure the gradient quotes along its membrane. So it must move around in a random fashion and then discover from by the field change, the field temporal change inside the cell, where is the right way to go. So I think, in my opinion, the easiest way to explain the tool is, for example, you have a sound source and it's a game. You and your friend are deafened, and you have a sound source. You must go to the source. So you have two microphones and your friend has only one microphone. So the only one microphone, you must move the microphone around, and according to the change of the intensity of this sound field in the microphone, you will say, for example, I move the microphone there, and then the field increases. So, okay, I will keep moving there until it decreases, and then I will move direction and explore the region. While in the chemotaxis, for example, you have multiple microphones, so you sense the field in a distribution, so you don't need to move around. If you have many microphones in a box, for example, you know which microphone is capturing more sound, which is capturing the less sound, and you can feel the gradient without moving, without displacing. Okay. Chemotaxis. Chemokinesis is more frequent in bacteria, small organisms. In cells, we see chemotaxis, for example, in Dictyostelium discoideum. This process is very important for the life cycle of this amoeba. Okay, so this amoeba can assume unicellular or multicellular configuration, and in order to regroup, right? In order to regroup, they secrete CAMP, which is a chemical in the medium, and then they communicate, they undergo chemotaxis, and then they can form bigger structures, multicellular structures. Okay. There's this other video here, which you can see. Now I don't remember if this is the field or the cell moving around. Don't remember exactly. Must check it. I think it's the, or maybe both the field and the cells. We don't know. I don't know. This is a complex cascade of reactions. So you have the chemoattractant receptor. It will receive an external signal, and it will translate this signal into some other reactions inside the cell. And when these occur in an anisotropic way, for example, you have more of this chemoattractant in one side of the cell rather than the other side of the cell, you disturb the equilibrium of those reactions, and the cell ends up polarizing. Okay, so you have many models, different models like this. This is not general. Okay, this highly depends on the type of the cell and on the type of the chemoattractant or chemorepulsant. Okay, you can experimentally you can see those fields, those molecules distributing on the cell. And get some clues of what is happening. But there are many things you need to think when modeling chemotaxis. For example, where is this signaling molecule? How do cells and tissues movements affect the distribution of the molecule? Because if the cell move inside this field, the cell will affect the field around. Okay. There are many questions here. For example, does the cell receive signal only receive the external signal only when contact with particular fluids or ECM or other cells? Does the spatial distribution of the receptors change in time because of some cellular process? Or maybe the number of receptors change in response to the signal level? Also, if there is a chemical saturation above the cell cannot respond anymore, or how does the cell transduce the signal internally? If there is a minimal level for the cell to respond, if the cell can move in the absence of the signal, if each part of the cell membrane responds separately, or the cell as a whole respond to the external signal, okay? If there is a relationship between the gradient steepness and the cell velocity. Also, if the cell moves deterministically in a chosen direction, or does it choose a biased motion and start mapping the field around like a bacteria? Not necessarily, Tamar, but you can expect they are complicated in the sense that there are many steps from the producing signal until the cell rearrangement. Okay, so the cell has to sense the signal, polarize, so the chemical reactions will polarize, the proteins inside the cell will polarize, the cytoskeleton will polarize, then the actin net, for example, will start to be polymerizated in other directions, in the direction of the gradient, for example. So they are complicated in the sense that there are many steps, and not all of those steps are biologically well understood. This is the sense. It's not in the sense that, oh, we'll have a hard time modeling chemotaxis. No, that's not the point. The point is that in detail, biologically, it is a complex phenomenon, like others biological phenomena, okay? For example, we talked about mitosis. Mitosis is very complicated, complex, but not in the sense of modeling. You can model in a simple way. It depends on the objectives of your model, okay? So Gilberto already talked about the... Yes, Itamar, yes. So Gilberto already talked about external potential. This is quite similar, but instead of a displacement in the pixel copy or in the center of mass of the cell, we will work with the gradient of the field. So, and this has many implications. So if the force is proportional to the field gradient, theoretically, you would expect that the cells would move infinitely fast in steeper gradients, but it's not true. Okay, there is a moment, there is a saturation somewhere. Okay, the cells won't move infinitely fast around our body. Okay, this would cause some problems. Also, we are not modeling cells causing advection on the fields. And also, we are not modeling cell absorption because sometimes the cell will have to absorb molecules of the field to produce the reactions inside. And you would expect the field to decrease a little bit, for example, but we are not modeling this as well. Okay. The Hamiltonian, the energy variation we are using to model chemotaxis is the following. So you have the lambda chemotaxis, which is a multiplier here. The increment in the energy comes with the negative sign here. And you test if the concentration of the target pixel in the copy attempt is higher than the concentration of the source pixel. If this is true, your energy will decrease. For example, suppose you have 3 cells here, and only the orange cell has this Hamiltonian here, okay, this energy variation, the chemotaxis. So, and the gradient is pointing to the right. It means that the pixels on the right of the cell, all of them has a concentration higher than the source pixels. So if you set a positive lambda chemotaxis, the cell will tend to walk to the right, okay? And you also can set this for specific cell types. So for example, if I say to the plugin, very informal, cell orange goes up gradient, which means positive lambda chemotaxis, okay? But only if the copy happens over green and medium cells, okay? So I have a green cell here, and the medium is around, and I have a blue cell here. So I only allow the copies to of the chemotaxis to happen over the green cells and the medium. What will happen is that the chemotaxis won't work towards the blue cell. It will only work towards the green cell and towards the medium. So basically, in this situation here, what will happen is that the orange cell will try to go around the blue cell, squeezing between the two, and probably pushing the green cell away. Okay? Any question on this? And this energy variation is proportional to the lambda, okay? So what does copy mean? So the copy is when the CompuCell algorithm is randomly picking pixels. It picks a neighbor pixel to offer a copy, and the copy is accepted or rejected based on the energy variation and based on the temperature or the fluctuations, okay? This is the copy attempt. It's the algorithm. Okay. So in this case, if the copy attempt is in the direction of the gradient, the concentration is higher. Then in this equation, if your lambda is positive, you will have a decrease in the energy. So if you have a positive lambda, you expect your cell to move up gradient. If you have a negative lambda chemotaxis, sorry, you will expect your cell to walk down gradient. Okay, let's move on. So I have an exercise for you. You have a cell, and I represented the concentration values here on the lattice, okay? And my cell has a chemotaxis behavior, okay, in this field, and it has a positive lambda chemotaxis, so it tends to walk up gradient. In which direction do you guys think that this cell will move to? Up, down, left, or right? According to this Hamiltonian. Down and right, down. Okay. So all those directions here in the blue arrows are favorable copies for the cell to do. So any of those copies are favorable. And for example, going up and left wouldn't be favorable. So the cell here tends to go down and a little bit to the right, as Darshan said, okay? But to the right only because of this pixel here, towards the higher number. Yes, Notion, yes. Okay, so the chemotaxis specification in CC3D starts in the wizard, okay? And in the wizard, you will find this window here where there are many configurations, okay? First of all, you can choose a chemotaxis type. We are not discussing the saturation and saturation linear. We will use another one to regulate the chemotaxis. So the regular one is basically the Hamiltonian that I show you. So this is the regular, okay? You can select the field that the cell will sense to do chemotaxis, okay? You select which cell type will respond to this field, to this gradient, okay? In this order: the field that causes chemotaxis, the cell type that will respond to the field, the lambda, which is the intensity of the chemotaxis, the medium, the chemotaxis towards, which means to which cell type will you allow the copies to be made. So if we go back to the example, here we are allowing the orange cell to go only to the green cell and to the medium. So this would be set in this slot here. So you would select the cell type that allows chemotaxis, and then click chemotaxis towards, okay? And then add entry. You will see all the specifications in the chemotaxis, okay?
Pedro, we do have one quick question. If you could very briefly explain what the saturation and saturation linear options are. Like, what do they mean?
Yes, basically the saturation and saturation linear are different functions that make the chemotaxis depend on the field intensity, not only on the gradient, because this simple Hamiltonian here, it only bothers with the difference between the two concentrations, okay? So it only matters if you have a gradient or not, positive or negative gradient. But in the case of saturation, for example, up above a certain field concentration, your cell will stop responding. So the chemotaxis will depend on the field concentration itself. Okay. So once you set your chemotaxis plugin, you will see this piece of code in the CC3D where you can change your lambda chemotaxis and set the cell types to which you allow your cell to protrude to, okay? And I have an exercise for you. I do step by step for this one because it is simple. But basically what we want to do in this exercise is set up a linear gradient with periodic a lattice with periodic boundary conditions, set a linear gradient, create a cell with chemotaxis properties, and see it go up and down gradient as we change the lambda chemotaxis, okay? So very quickly here, CC3D project, new project, we have our, okay. And here, Chemo Pedro.
I'm going to jump in here for 1 second and address, excuse me, something. So we've had a couple of people having issues today with simulations with periods in the file name. I just want to say real quick, if you're using the numbers to keep track of your simulations during the workshop, so like 3.1.2, It's recommended not to use periods in the file names because they don't always get parsed cleanly by the Python interpreter, especially when those get auto-generated into class names, because periods are used as separators there. So I recommend using dashes or underscores in the file names. NanoHub will crash and disconnect a lot of times if you have periods in the file names. So
You
just a
also
heads up
can
there.
write. You also can write the way I wrote, for example, 3.2.1. But you may think, oh, this is not a dot. No, this is a dot, but this is a big one.
Yeah,
Okay.
so avoid periods and spaces and any other special characters. There's be one conjoined word. Dashes or underscores is the best way to do separators. Anyway, that's all, Pedro. Go ahead.
Taxes is funny. Okay. Next, then here reduce the lattice 200, 100, like said in the exercise. Set periodic boundary conditions in X and Y. Next, add a cell, for example, cell. Next, create a field. So in the exercise, the field is named oxygen. Let's keep it this way. Selecting the fusion solver, add the field. Next, in cell properties and behaviors, please check contact. Please check volume and chemotaxis. Can I launch the poll, Hayden?
1 second. I think, James, did you grab the data from the last poll already?
Yes, so I can launch them, right?
Yes, go ahead.
Okay. Okay, fine. If you have problems, please type in the chat, call for help. So now we reach the Chemotaxis plugin. Okay. What you need to do here is leave regular as Chemotaxis type, select oxygen, select your cell type, which is cell, set a lambda to 500. Then keep selected medium as a cell type that your cell will protrude to. So your cell will invade medium pixels. And click Chemotaxis towards. So the medium appears on this box here, okay? And then hit add entry. Make sure your Chemotaxis is like mine. So oxygen, cell, 500, medium. Okay. This is the end of the configuration. Finish. Open your file. Okay. Let's first, before we run, let's take a look in the Chemotaxis plugin. Let's see how it looks. So go to your XML and take a look at the Chemotaxis plugin. It has the specification for the field type, I mean the field name. You have the cell type that suffers the chemotaxis, the lambda, and which pixels are allowed to be copied to. So for example, in this case, our cell will copy itself towards medium, and because of positive lambda, it will move up a gradient. So now you can run the simulation. And see what is the result. Oh, so the result is not what we expected. Why? Because we need to set up the initializer and also change our volume constraints so our cells don't die. Okay. So go to your volume plugin and change your target volume to 300 with lambda volume 10. Like Gilberto's simulation, okay? Then go to the uniform initializer and initialize your cell in the center of the lattice. So it will be from 90, let's say 95 to 105. Sorry, 105 here. Okay. And from 46 to 56. Since our X dimension is 200 pixels, our Y dimension is 100 pixels. So we build our cell from 95 to 105 in the X coordinate, and from 45 to 55 in the Y dimension, okay? And set the width to 10. So we have just one cell, okay? And then you run. So the boundary condition seems to not be working, since we wanted a linear gradient. It's not a linear gradient. Yes, because always when you start a simulation into edit with fields, you need to fix your boundary conditions. So go to the boundary conditions and set constant value to 1 and 0 in the X direction. And the constant derivatives, you set 0, 0 in the Y direction. So this will produce a linear gradient for us. Okay. Also, our cell is secreting in line 73. So you may want to comment this line. Also, we have decay coefficient. So in order to achieve that linear gradient, we cannot have decay. So set the decays to 0 as well. So I asked you to change the boundary conditions, constant value 1, 0, and constant derivative 0, 0. Then I asked you to comment the secretion in the diffusion field. And then I asked you to set decays to 0. So the boundary conditions are constant value 1 and 0 for x, and constant derivative 0, 0, 0 and 0 for y. So boundaries, constant value constant value 1 to 0 for x, constant derivative 0 to 0 for y. Okay, like in my code. The initializer values I set to 95 to 105. And for the y component, 45, 55. The target volume and lambda volume I picked is the target volume is 300 and the lambda volume 10. What is the target volume? I put in the chat, okay? So target 300, lambda 10. Here. 10 and 300. Now I have my simulation running and it seems okay. So I want to know if you guys got something similar to what I got.
Yeah, so my simulation is running, but the moment I changed from the cell field to oxygen, I'm not getting what you're getting.
I didn't understand what you said, sorry.
So my simulation is running. For when I change it to cell field, I can see the cell, but the moment I change it from cell field to oxygen, I'm not getting what you're getting. Yep, yeah. I did hit run again. Okay, boundary conditions. You have my x-axis is 1 and 0, y-axis 0, 0. Yep.
But the gradient is on the horizontal surrounding.
Oh,
Yes, The color are on the x-axis. Yes.
No, I'm saying mine does not look, mine's opposite of yours. So it's like if you turn yours
90
90
degrees.
degrees to the left, mine looks like that.
So probably what you've done is in the boundary conditions, probably you set constant value for the y and constant derivative for the x. Or you didn't put 1, 0 in the constant value for x and 0, 0 for the constant derivative on the y.
Yeah,
Something
I have those values. I have the same values as you.
And you are sure it's constant value for x, constant derivative for y.
You have the same thing.
Yes, 80, line 86. Yeah.
And in the player, does it appear x here and y here? Is it right?
Yep, it's a yep, X and Y. Yeah, but I can, the cell and then these it's not screening anything. So I just have a blank blue screen with nothing.
Sarana, if I didn't help with you,
Oh,
you
yes,
with this.
it corrected.
Ah, okay.
I just made sure I saved it all. It's looks like yours now. Thank you.
Okay, okay, nice, nice. And
Yeah, I think I would like to join a breakup room.
okay, okay,
Breakout room.
fair.
Oh, it's my mistake.
So you guys notice, for example, that it takes a while, a good while for the field to diffuse and to achieve the steady state, but you can see the cell doing chemotaxis. One thing you can do, for example, is to invert the sign of the lambda parameter. So here in the player, see, look at my simulation here, my step by step here. You open in the model editor, you open the chemotaxis plugin, the chemical field, chemotaxis by type, and here you have the chemotaxis towards medium for cell type cell. And here, if you change the sign of the field, your cell will move the problem is that my cell is sticking to the boundary because I didn't set periodic boundary conditions. So I will pause here and I will check if oh, it is periodic. Ah, I know what's happening. I know what's happening. I just need to increase this value because probably the cell is sensing the blue on the other side. So if I add one more 0, for example, yes, it should go to the right now. So if your cell was sticking, it was sticking on the boundary because it feels the gradient on the other side and it doesn't want to get out anymore. And if you keep changing the sign, your cell will move left, right, left, right, left, right. Now I want to know if you guys got this result. So I will launch the poll again. So one person needs help. We have some breakout rooms running now, so if you need special helps, please join. Feel free to join the breakout rooms. Okay. And now, go ahead and increase the lambda and see what happens to the cell. Then invert, it moves to the other side. See what happens to the cell when you increase the lambda. Now let's increase more, even more. So I multiplied by 10. It was already 50,000. Now it's 500,000. So you may see that although we are increasing the lambda value, oh, my cell is about to die. Although we are increasing, multiplying the lambda value by 10, we are not seeing the speed of the cell multiplying by 10, right? At least I am not seeing. I don't know about you. I've been working a lot. Maybe I'm not seeing stuff correctly. And now I have more than one cell. Okay. One cell divided by 2 should be an unstable system because of contact energy. So eventually it will collapse into one cell again. So I will pause here before it touches, and I will multiply by 10 again and invert the sign. And you see that the speed doesn't increase by a factor of 10, although we are increasing our lambda chemotaxis by 10. This is because, as Gilberto already taught in his lecture, there is a maximum limit for speed in cells in CompuCell. You cannot run faster than 1 pixel per Monte Carlo step because the pixel copy range is 1. I will launch the poll again, asking you guys if you could change the lambda values, multiplying by 10, changing sign, and see this behavior, that the cell speed doesn't change accordingly, okay? You can multiply by even higher numbers, and you will not see the cell moving faster and faster, okay? Okay. So I don't think we will have time to set up a plot. So I will show the plots. Okay, this is the instructions. I went over it already. Okay. So now it's theory again. What happens if we put our cell in a very, very steep gradient? So this is a problem that the regular chemotaxis has. That regular chemotaxis has in CompuCell. which is if you have an extremely steep gradient, actually, I should say, an extremely steep varying gradient. Okay, so for example, an exponential decay, your cell may disappear because the forces acting over the cells are too high. Okay, are too different in the two sides of the cell. So your cell can die because of a exponential gradient, a very steep exponential gradient, for example. Okay, so we have adaptation for lambda chemotaxis. For example, the logarithmic scaled chemotaxis, which is very useful in biological situations. Because, for example, if your cell respond to a certain gradient the same way for all gradient values, it won't respond well at larger distances. So, for example, if you want a macrophage to sense a bacterium at a long distance range, longer than side by side, obviously. So, for example, 4, 5, 6 cells radius of distance, you could use, for example, the logarithmic scaled adaptation for the lambda chemotaxis. So the cell, even though it is in a smaller gradient, it will still respond effectively to the gradient, to the field, to the sign. Okay, and if it is in an extremely steep gradient, it will behave the same way. It will not apply giant forces because of a giant gradient. Okay, so this is like, let's say, a good way to control gradient variations across the simulation, and you also prevent your cell from dying when going from a region of low gradient to a region of high gradient. Okay, so we are going to implement this. And
Pedro, I have a quick question, if that's fine.
Mhm.
So you showed that you can change the boundary conditions of the XML file. Is there a way to do it at the Python? Because you were moving it up and down. I was thinking if you can put at your highest state, which is 1, a sine function, then you don't need to do it. It'll just oscillate. The cell will keep on oscillating with the frequency. Is there a way you can do it on Python?
I never done this. Done it.
Yeah, I
this
cannot,
way.
for some reason, I'm not able to access the boundary condition thingy over on the Python side. It's only on the XML.
Yes, I really, I don't know. I don't know if you can access the boundary conditions. I don't know.
Okay.
I never used. I never needed. So I'm sorry.
Yeah, sure. Thank you.
Probably James will know this better. So this is the exercise. You basically start from the simulation we have. You set an initial concentration equilibrium at an exponential, okay, and set a proper decay for it, okay. So the decay you set, the global decay you set for the simulation must be used together with the diffusion to set here the initial equilibrium condition, okay, in this exponential. And then you get the proper syntax for the logarithmic scaled chemotaxis in the manual, in the CC3D manual, okay? So I will post the link for the online manual, so you can, and then you search there, because you also need to learn how to search CompuCell syntax by yourself. it's not this one. Yes. I'll post the link to the manual on the chat. Sorry. Not quite it. Yes, the link to the manual is on the chat. So try to find the proper syntax, the proper way to implement the logarithmic saturation chemotaxis. Implement this in your code, okay? Then set a proper initial condition with decay coefficient and an exponential for the equilibrium, the initial concentration, already at the equilibrium, okay? And then run. And also test with the regular and with the logarithmic saturated. See how those two behave. Compare the two. And the next 30 seconds, I will get some tea because my throat is getting sore. The way I do was again who was asking about the boundaries.
It was me, yeah.
Barrett,
Hi.
okay.
Yeah.
The way I do this personally when I am treating gradients and I want a specific gradient and I want it to vary, for example, in a sinusoidal way, for example, a gradient doing this
Right.
or doing, I don't know, this, anything. What I do is I set the diffusion coefficient to 0.
Okay.
And then I build the field in the Python.
I see. How does that
Otherwise,
help?
what? Sorry,
How does that help? How
I
do you
didn't.
get like a sinusoid using that?
Using
By
Python. So I set field values in the Python code. You
okay,
can,
that's cool.
yes. So
You just make a function. Yeah, you just
yes,
make a theta and then probably a numpy array
yes.
showing the value. Okay. Thank
You
you.
simply say field at coordinate equals 0 equals 1.
Mhm.
So you reference your field, for example, real field, self field, Barrett.
We can't see what you're doing.
I am sending the chat.
Okay, I think you should move on probably.
Okay. How many time do I have still?
15 minutes.
Okay. So the difference, if you were to make a plot of the cell position, is that for regular chemotaxis, the sorry, Monte Carlo. Okay, for regular chemotaxis, the position will vary more. The speed will vary more and more as you get closer to the high steep gradients, and then the cell will die when it reaches the higher steeps, the higher gradients. And then in the logarithmic situation, the cell move basically within the same fashion until it reaches the barrier. You don't overcome this, I think. So you can change your lambda parameters and see what happens. And there is this very beautiful simulation, which is the self-constructed gradient that I will build with you guys. So there is, yes, okay. So this simulation of the self-constructed gradient is a way that you can make the cell enter a random motion because of a field around itself. Okay. So basically, what's the idea? You have a nutrient on the field and an amoeba, for example, and then the amoeba starts uptaking the nutrient, and because it has to find more nutrients, it will have a chemotaxis towards gradients. So the amoeba will uptake field here and then move there because here you still have nutrient, and it will move in a random fashion, trying to find more nutrients. So this is the idea, and we will build this simulation together. Okay. So self-constructed gradients, 100 by 100 pixels, lattice dimensions. Okay. Boundary, periodic boundary conditions, very useful for this simulation, so it doesn't get stuck. Then the amoeba, for example, the field, the nutrient field. Then select contact, volume, chemotaxis. Okay. Are you with me, guys? Okay. Then in the Chemotaxis plugin, set lambda chemotaxis to 200, and amoeba will follow nutrient towards medium. Okay, so hit chemotaxis towards and add entry. Okay, leave it regular. We don't need the others. Okay, next. Did you set up the simulation wizard? Launching the poll again. Okay, fine. Next, and configuration complete. Now we need first to fix our boundary conditions. This is the first thing. So fix the boundary conditions and set them to periodic. Okay. So comment this, comment that, uncomment periodic, and uncomment periodic. In the boundary conditions. Periodic in both. Then create only one amoeba. So if our lattice is 100, let's create from 45 to 55, 45 to 55, and width 10. Okay. Same thing. In the middle of the lattice, just one cell. And also change the volume. So in this case, let's put 100 pixels cell. And lambda volume, we can let it be 2. I don't think the cell will die because of that. We will see. Then,
So what was the target volume?
sorry?
The target
The target
volume?
100. Okay.
Okay.
100 target volume. Then in the diffusion solver FE, we will set an initial concentration of 1 in all places. So all pixels in the medium will have initial concentration 1. Then set the global diffusion to 0, since we are treating this nutrient as a very heavy substance, or a very sticky substance, which is deposited in the substrate, so it won't move. Okay, amoeba must find this substance. Okay. Now the global diffusion, the global decay must be 0 as well, because if nobody eats the nutrient won't disappear in the medium, at least in the short term. But we want some decay on the amoeba, okay, and it suggests 0.001. So the amoeba will eat the nutrient. Okay, so that's why we are setting a decay coefficient in the amoeba. And then comment the secretion. We don't want amoeba to secrete. Okay. I will relaunch the poll to see if you guys are with me. Okay, you guys are good. Many people doing the exercise, many people don't. If you have problems, please type on the chat. Okay. So initial concentration 1, decay 0, diffusion 0, the globals. And he also, no. He suggests specific diffusion coefficient to 001. So 001, the specific diffusion coefficient, and 0.1 for the decay coefficient. So I'm sorry, my mistake. Okay, yeah, you can also help each other on the chat. Then let's run and see what happens. As James said, this is very important for metastasis, for example. Oh yeah, it's working. Ah, I thought it would crash. So this is a very interesting simulation. You can see that the cell is moving around, trying to find more nutrients. Okay. So please tell me if you could reproduce this behavior here. I'm relaunching the poll. Serena, your cell isn't moving. Probably we have a problem in your parameters.
Did we resize like the X and the Y?
Resize the X and Y, you mean the, yes, you can. You go to, let me show you. You go up here in the CC3D specification, the POTS specification, and here you have the dimensions 100 and 100. You can set it to, let's say 50-50, 200-200. You can change this, yes. Yes, Barrett had a good idea about what can be the problem. So if you have secretion, if your amoeba is secreting, it won't move because it's always generating its own resources. Okay. Where is my cell now? I stopped the simulation. So
No, I commented that one out.
let's see then. Check if you set the specific diffusion coefficient for the cell type amoeba to 0.01. And also diffusion coefficient to 0.1. Those specifications here must be similar to mine at least.
Itamar has a good question that may be worth going into more detail in the Q&A session later because we're running out of time here, but maybe a brief explanation of how cells know to avoid collisions. Never mind, James is responding in the chat. But yeah, we can talk more about that in the Q&A possibly.
Okay. So I want to show you my version of this simulation to show you what you can do with this generated gradient. So where is the CompuCell stuff? CompuCell here. So I made a post in CompuCell group. Try to find it here. It's the last post. So you can get some nice patterns here if you have a multicellular structure, for example, using this self-generated gradient and allowing medium to constantly secrete the field, you can get this type of aggregate organization where it tries to maximize the nutrient absorption for all cells. And also there's a very interesting simulation as well, which you can check in the NanoHub. So I will show how you can access this simulation. Is a very, very nice simulation of a macrophage pursuing bacteria, because bacteria is secreting some substances in the medium, and you have those red blood cells in the medium, so the macrophage needs to squeeze between those cells. So if you go to NanoHub, for example, I will go full screen here because otherwise it's going to be difficult for me to. So CompuCell main tool. And I already have the simulation loaded. I will give you the path to the simulation. You must start from your main folder. So your folder, CompuCell demos, models, and bacterium macrophage. So this is the path to the simulation here in NanoHub. And it crashed, obviously. So terminate. CompuCell main tool, launch. It's already loaded, but I will show you the path here live. So open simulation file, you need to go to your folder, then CompuCell3D demos, then demos, then models, then bacterial macrophage periodic, and load the simulation. And hit play, and you can see the colors are different, but you can see that the macrophages are going after the bacterium. I will resize here a little bit for you to see better what's happening. If you didn't load in your NanoHub. And you can also, instead of seeing the cell field, the ATTR field. So the cells are secreting something. The macrophages go after the bacteria. And you can also introduce other interactions between the macrophage and the bacteria, so that the macrophage eats the bacteria. Okay. So that's it for my lecture for now. Okay. I appreciate your attention, your patience, and I'm very, very happy to have given this lecture today for you guys. Okay. Please fill up the questionnaire. It's very important for us to keep track of lecture quality and exercises, etc. Okay, give your opinion at the end.
Yeah, can I ask a question?
Sure, go ahead.
Yeah, so if the movement of the cell is really slow and then you want to accelerate it, how do you do that?
One way, first, you can depend on the movement mechanism you're using. If you're using Chemotaxis, are you using Chemotaxis?
Yes.
Okay, so if you want to increase the cell movement, you can first increase the lambda parameter. You can second decrease the lambda volume. You can third decrease the contact energy surface between the cell and other stuff. You can also say that actually your cell is moving at a high speed, but by resizing the time scale of other stuff around. So for example, let's say you have a cell moving and another cell dividing. So instead of making the cell move faster, you make the other cell divide slower, so that you can rescale all the simulation time and say, oh, no, this is really fast speed here. But you cannot cross the barrier of 1 pixel per Monte Carlo step.
Okay.
May I ask about the Hamiltonian?
Of course, yes.
Okay, I have two questions about it. One is it the Hamiltonian for chemical potential, or it's like chemical potential? It's not like potential energy plus kinetic energy that I'm used to from physics. That's first one. The other one is, since you are playing with lambda values, the question, natural question could be, showing my ignorance, that it is a function of time and space. That lambda is fixed, right? You either increase it or decrease it or keep it constant, but it could be like over the grid or over the lattice, and during the process, it may change.
Yes.
So does it make some effect?
Yes, you
Are we
can.
considering it?
Yes, you can take the lambda value and change it in Python. So you can make it change with time, with position. You can make all those type of changes.
But I'll have very different behaviors, no?
Yes, you will.
Okay, what about the first part with the chemical potential, Hamiltonian?
Yes, so to fully explain the Hamiltonian of pots, actually, James is the best one to answer, but I will try, and James will correct me because I will be wrong in what I say. It all begins with the Ising model. So you have the ferromagnetic model for spins, and they interact via the coupling Hamiltonian, where you have the term for aligning magnetic moments for spins. So then you develop this Ising model for a Potts model, where you have multiple types of spins. So you don't have like minus half plus half. Now you can have, for example, 0, 1, 2, 3. And then you say pixel 0 is medium, pixel 1 is cell. and then you only allow interaction between along the borders. So this will make everything totally different. And then you start to build your own energies because it is a completely different universe. So how we will set, for example, energies for round cells? So then probably James and his colleagues came with the idea of the contact energy. And really, James should tell us those stories. One day I will ask James how was this process, but this question is a question that I also have. Okay, so one day James could tell us the story of how he and the others built the pots, the cellular pots model, because it's an entire different universe, and it is brilliant how it works. It's all the concepts from the physics of energy, etc., but you create new types of energies to mimic behaviors that you don't find in any other classical Hamiltonian that you see in physics books. So it's brilliant.
Surprising and fascinating. Now,
Yes,
James
exactly.
answered my question to you before, how the cells know to avoid each other, by saying that they generate local gradient that repels any other fellow that comes near. Now, do we have that in the equations or in the whatever notebook in CC3D? Do we have it installed explicitly, or that just happened?
Well,
Go ahead.
the easiest way to do is with contact energy. If you set a high contact energy, you are already preventing direct contact. But you can also implement local fields for the cells, and with a high decay, so they decay spatially very fast, and then some chemotaxis behavior for them to stay apart each other.